Welcome to Heart of Mathematics. This is Poincare's conjecture. So in the last video, we talked about the idea of topology and graph theory. And so this goes into a little more of topology and algebraic topology, and specifically to Poincare's conjecture. So let's recall a little bit of topology. So topology is a study of connectedness in space, so really how things are different or alike under distortion. So a homeomorphism, which is a function, is a distortion from one space to another that's continuous and invertible. So remember that the idea of invertibility is that we have a one-to-one and onto function. So I have to have a unique one-to-one connection, so I know where things go and I know how they go exactly. So recall earlier in the semester, we talked about people and their beverage choices. Everyone has a beverage and everyone's beverage is unique. So the idea that the distortion is continuous means that it's nice and smooth, and we can see that it happens nice and smooth. There's no jumps or cuts or anything sharp. We can think of like a continuous smooth path. Nothing crazy is happening in our distortion. So an example of a distortion we can think of as is we have some sort of crazy shape here. This is a homeomorphism between a nice circle here. You can say this is a homeomorphism. And so I always abbreviated in grad school homeomorphism as homeo with a little m from morphism. And so this is a nice, pretty homeomorphism. But the circle is not a homeomorphism between a circle with a hole in it, because I can't distort my circle into something that has a hole in it. In the same fashion, I can't distort my squiggle into something that could have sharp edges into something with a hole in it. But I do have a homeomorphism between something that has the sharp edged box with a sharp hole in it into something smooth with the hole, because remember, I can squish my edges out nice and smooth as long as I have a nice pretty function, which we can talk about what those are, continuous pretty functions that do this, to smooth out those edges, smooth it into a nice pretty circle. So homeomorphisms turn oddly shaped pieces into nice pieces to work with, but they have to preserve numbers of holes, and we saw that a little bit in the last video. So Poincare, who was a French mathematician, studied bounded spaces, which sometimes we call manifolds. So manifolds are just different sorts of spaces in topology land. And so bounded spaces, unlike planes, look like spheres. So bounded being that they have kind of some sort of closed property. So a sphere has a boundary to it, right? Or a torus has a boundary to it, or a cube. Some of those properties there, they have boundaries, right? There's, kind of think of them as holding them. They don't go off to infinity. And so a sphere is not homeomorphic to a torus because, again, like the previous video, we can't puncture our sphere because that's not a property that we're allowed to do. So what we can do is that if we had our torus and we took our sphere and we just rearranged the handle, right, and we made a little handle here on our sphere, like one of those little bouncy balls that you had when you were a kid. This is now homeomorphic to the torus, because we can rearrange, we can stretch, we can flatten out, we can expand parts of a torus to get to the sphere, but these are not necessarily the same thing as the sphere. So the idea of loops is that if you draw a loop on a surface and shrink it down to a point, then the loop is what we say is contractible. If any loop on the surface, you shrink down to a point. If you don't, then you have a hole somewhere in your surface. So for example, if I have this loop here, if I have an open circle here and I have this sort of loop here, then I can give my loop a direction if I want. I can take this loop and I can take my same circle and I can shrink this loop down, down, down until I can get smaller and smaller and smaller. Let me actually move this down so we can see a little bit more of a progression here until I get to just a single point. And so if I take the same circle, but I just add a hole to the center of it, some of my loops, let me make my 3 loops here. So if I take some of my loops and I have a loop over here, I can shrink it down and it's down to a certain point, and that's fine. But if I have a different loop, let's say that goes around this hole, and I shrink it down, and I shrink it down as tight as I can, but I can't get it to a point, I say that loop is not contractible. So if I have a loop that is contractible and a loop that's not contractible, then, and it's different. So if I have one space where I have a loop that has all contractible, or all loops are contractible, as in this first example, tractable. So in the first example in blue, every loop is contractible. No matter how I draw my loops, I'm going to shrink down to a certain point. But in my second example, there are loops that are not contractible. So that means these two spaces are different. So this is an example of a homeomorphism. A homeomorphism is an invariant. It doesn't change under this distortion. So the idea of contractibility is what we call an invariant. It won't change no matter how I stretch or twist this. That loop around that hole won't change under this homeomorphism. So homeomorphisms preserve homotopy, and two spaces we say are homotopic if you can deform it from one to another. So Poincare's conjecture says that any simply closed surface is homeomorphic to an n-sphere. And now an n-sphere is just an n-dimensional sphere. So this right here is an n-dimensional sphere. We can visualize a two-sphere. A two-sphere is what we are used to thinking about. A two-sphere is our general sphere. A three-sphere, you saw the video with the little fish. And the idea is that conceptually, we're like, okay, so closed means that it's bounded, right? It doesn't go off to infinity anywhere. Simply connected means there's no glued spots, there's no cut spots, there's no kind of crazy intersections. And I can get from one point to another in a straight line. And I'm just looking at the surface. And Poincare's conjecture says that I can manipulate this surface, this closed, simply connected surface. I can squish it, maneuver it around such that eventually I can get to an n-sphere. This has been proven for a two-sphere by Poincare, and only recently, like in the 2000s, has it been proven for a three-sphere by Perelman, who's a Russian mathematician. So this is a pretty cool thing, and it's a pretty cool thing in mathematics, and it's a pretty cool thing to leave this class on. So if you have any questions, feel free to ask me. It's not my great area of expertise because I'm not an algebraic topologist, but just know that by even understanding a little bit of this, you're working in graduate level material right now, which is pretty awesome. So keep that in mind.